I welcome you once again to this course on microscale transport process. What we were discussing is various manufacturing methods to form a microscale device, and I mentioned that the traditional micromachining process that is typically employed in mechanical fabrication, that can always be employed here as well. However, there are alternative routes people are looking for, and these photolithography technique, that is one such method which has been borrowed from semiconductor fabrication processes. That the method has been tailored for fabrication of microscale devices. So, the essence of this technique has been taken from semiconductor manufacturing. However, the technique has been tailored for these fabrication of microscale devices. Now, we need to discuss first how this photolithography works. Basically, you have to create a channel on a silicon plate. That channel will act as a micro channel. Now, when it comes to making a channel of aperture or of width 1 millimeter, you can always do it in a conventional, in a traditional machining process using something called a lathe machine. However, when it comes to making a channel which has width of 1 micrometer or somewhat width of the order of 1 micrometer, it is difficult. I mean, 1 micrometer is a very small dimension. So, the method that is commonly employed to make a channel of 1 micrometer on a silicon substrate is that a light source is there at the top. Then there is a so light emanates from there. Okay, light of certain wavelength emanates from there, and then you have a instrument called a mask aligner that positions a mask here. So, this is a mask. This is basically a plate on which certain pattern is there. Okay, let us say a circle is there. All right, and then you have the actual silicon substrate which comes below the mask. So, this is the actual silicon substrate that is there. Okay. Now, this silicon substrate is coated with a photoresist material. That means, this silicon substrate is coated with a polymer. That polymer has some photo solubility. That means, it is this polymer, if it is exposed to light of certain wavelength, this polymer becomes soluble to certain solvent, or it could be otherwise. If it is exposed to light, then it was originally it was otherwise soluble to a solvent, but now after the exposure this solubility is lost. So, it could be either way. That means, this polymer is sensitive to light, okay. And if this polymer is exposed to light of certain wavelength, of course, then the solubility pattern of this polymer, solubility property of this polymer gets altered. Now, you are exposing this polymer, now you are coating this polymer on the substrate. So, this substrate is coated with this polymer, and then you have a mask, a portion of it which is dark. How do you make it dark? That I am coming to it. Now, as the light comes there, light can go through this part of the mask, but not through this circular portion. So, you will see a pattern on the plate, on the substrate. That means, this portion would be these portions would be exposed to light. However, this portion will remain unexposed because of this pattern. All right. So, now if you go back and dissolve this polymer to another solution, then what you see is, depending on what type of polymer you have chosen, either this part of the polymer will completely dissolve, leaving a layer here, or it could be that this part of the polymer gets completely dissolved, leaving the layer elsewhere. All right. Now, what you do is you dip this substrate. It is exposed preferentially to some places and not exposed in other places. You have coating of polymer in some places and you do not have coating of polymer in other places. So, now you dip this into an etching fluid. The idea of etching fluid is this etching fluid will have a chemical reaction with silicon and dissolve this, and the product goes back to the solution. So, if you leave it for some time, this chemical will attack the silicon substrate wherever the silicon is exposed and eat away the silicon. So, it forms a groove on the silicon wherever it is exposed, wherever the coating is not there. So, it will form a groove there, and then as it will form a groove on the silicon layer. Now, depending on how long you keep it in the etching solution, it could be forming a groove of say depth so and so micrometer. Okay, if you dip it for double the time, you expect that there will be more etching happening. So, this is a technique. So, once you are done with that, then you can remove the polymer that is left out. So, this is a technique which is considered very accurate, and it can give a channel of dimension of the order of micrometer. So, let me now read these what I have on the slide. This is photolithography mask. First is photolithography mask. The mask is the one that I have in the middle of this figure. In this figure, I have the middle one, that is the mask. That is what we are talking about. What we are talking about here is the mask, and the bottom one is the substrate, silicon substrate, on which you want to make the channel, and the top one, this is basically the light source. Now, photolithography mask protects certain part of a resist from illumination. The spectral band of the illumination is 300 nanometer to 450 nanometer. Plates of quartz on which deposits of chrome forms a pattern. So, basically this mask is a plate of quartz on which deposits of chrome forms a pattern. So, the pattern, that circle, that is the pattern there. Okay. That could be just a line which will form a channel. So, that pattern is formed by chrome deposit. Deposition is made using electron beams. This deposition is done on this plate, on this quartz plate, by electron beams. A less precise one, a less precise photolithography mask, not a good mask, but something which you students who are dabbling on this, who are just trying to understand the process, a less precise one can be just a printout on plastic transparency sheet. So, there are plastic transparency sheets available on which you can take, using a special printer, you can print the diagram. For example, here it is a circle. So, you can print the circle, make the inner portion dark and print it on a plastic transparency, and that may act as a less precise mask. Now, the photosensitive resist, I said that there would be a coating of polymer on the substrate. There would be a coating of polymer on the substrate, and that polymer should have certain property in terms of photosolubility. That means, when it is exposed to light, its solubility property, it changes. Now, photosensitive resist, I see what I see here is mask is placed on top of a substrate covered by photosensitive polymer. So, this polymer comes as a this substrate is covered by the photosensitive polymer. How we cover it? There is a special technique to it. I will discuss this in a moment. Next, what you do is substrate is put under uniform beam. After the uniform coating of substrate with photosensitive polymer, the substrate is put under uniform beam, right. That is what we discussed, photolithography. The regions appear on the polymer as lit or dark as per the pattern that had been designed on the mask. This is referred as pattern transfer step. Instead of a circle, say instead of a circle, if we would have had a symbol A here, If you would have had a symbol A here, we would have seen a replica, we would have seen the pattern transfer happening to the silicon substrate by this method. So, that is what we are talking about, is what we are referring as pattern transfer step. So, regions appear on the polymer as lit or dark as per the pattern that had been designed on the mask. So, you must understand that pattern is not transparent. Pattern, you are making it by a dark ink, right. You are taking a printout. Pattern is not allowing light to pass through it. The rest of it, anything other than the pattern, that is allowing light to pass through it. So, that is how the pattern is created and pattern is transferred to the substrate. Light sets changes in photosensitive polymer and make the polymer soluble to certain solvent. Upon dipping in the solvent, the polymer in the lit portion is dissolved. The exposed portions of the substrate undergo chemical attack from etching fluid. So, you dip after the exposure by light, then you go to then you dip this substrate coated with polymer, you dip this substrate into certain solvent. So, upon dipping in the solvent, the polymer in the lit portion is dissolved. That is one type of resist where the lit polymer in the lit portion is dissolved. Okay, the places where light has hit the polymer, in those places the solubility, that property has changed, and so that portion is getting dissolved. Now, once it gets dissolved, means those portions are getting exposed. So, that surface is getting exposed. The exposed portion of the substrate undergo chemical attack from the etching fluid. So, when you dip this substrate after the dissolution of the polymer, when you dip this substrate into the etching fluid, then the etching starts, but the etching happens only in the places where the substrate is exposed. Next is, depending on the time over which the substrate is kept in the etching fluid, the exposed portions are etched to a depth. So, how long you keep it in the etching fluid. So, gradually you see the etching taking place and a depth develops in that channel. Now, how do you coat the polymer? How do you coat the substrate with the polymer? There is a special technique which is used. The method goes by the name spin coating. Okay. The spin coating is the method that is employed to coat the polymer on the substrate material, because this coating has to be very uniform. It is absolutely necessary that the coating is very uniform, and certain properties of the polymer are also required. What type of property? For example, this polymer itself has to be transparent to light. If there is a thickness and the upper portion of the polymer is the property of the upper portion of the polymer gets changed because of light, but light cannot penetrate all the way into the depth of the polymer. So, then the lower portion will not change, the property will not change there. So, you want the property to change everywhere over the entire depth. So, that for that to happen, this polymer has to allow light to pass through it. So, there are certain properties of the polymer. In fact, these polymers are made by large business houses, and they have spent a good amount of research developing these polymers, and they found the best polymer that is their objective, to find the best polymer that suits the purpose. Now, photosensitive polymer is deposited in a thin layer on a solid substrate of silicon or glass. So, substrate is either silicon or glass when it comes to photolithography. Okay. Silicon is a crystalline material. I mean, we will discuss briefly what is silicon and what is the difference between silicon and glass. Silicon is a crystalline material and glass is an amorphous material. Crystalline means there is an arrangement when it comes to the atoms, but amorphous means they are all tangled up. I mean, there are certain, and these properties will come into picture because you are creating a micro channel on this material. So, all these properties are important. So, you have a photosensitive polymer deposited in a thin layer on a solid substrate of silicon or glass. Three stages of the coating process are distribution, spreading, evaporation and solidification. What is this spin coating process? What you have here is, you have the wafer. This is called the wafer. Wafer means it is a thin silicon substrate. the width of it is 500 micrometer, and it comes in, say, the other dimension is typically 4 inches. Okay, so this is a silicon substrate. It is obtained from a silicon monocrystal. So you can expect the crystalline arrangement of silicon maintained there. Silicon has a particular crystalline arrangement. I will in a moment we will discuss this, what is the crystalline arrangement, because this crystalline arrangement comes into play when you make these, when you start the etching process. Okay. So these, so for the time being you take it that it is a wafer. So wafer means it is a thin plate. The size, the other size is 4 inches, the other dimension is 4 inches, and the thickness is 500 micrometer. So you have this silicon wafer, and this silicon wafer, on this you want to coat this silicon wafer by the photoresist material, which is a polymer. Okay. So what you do here is you have a resin feeder. You have a resin feeder. This is the feeder through which you inject the polymer. So this is the place where the polymer is put on the silicon. Okay. And then what you do is you rotate this wafer, rotate at a really high RPM, initially maybe 1000 and then going all the way to 8000. You rotate this wafer at a high RPM. Moment you rotate, what will happen to this resin material? Because of centrifugal force, it will start spreading out, right? So next time when you see, when you start rotating, suppose this is the wafer and this is the chuck, this is called chuck to hold the wafer. Now when you start rotating, when this starts rotating, you see that there would be a thin layer being deposited, thin layer forming on this substrate, because by centrifugal action there would be a radially the resin material will start flowing, right. However, there exists something called an equilibrium thickness. Equilibrium thickness. What could be this equilibrium thickness? And more important, equilibrium thickness is if you rotate this material for some time. In fact, I have defined on the slide this equilibrium thickness. The thickness achieved after spinning for few minutes with evaporation. The thickness achieved after spinning for few minutes. So that means you spin this wafer with the resist material on it, and then you spin it and you see there is a coating developing. So this thickness here, this thickness is referred as equilibrium thickness. So with evaporation of solvent, viscosity increases. With decrease in radial velocity, viscosity increases for shear thinning fluid. The fluid stops moving beyond a distance. So you understand why you have an equilibrium thickness, because if it is just water, you think of putting water on a rotating substrate, on a spinning substrate like this, and you have a centrifugal force. You expect that you have created a driving force and water will be simply thrown out. But here what is happening is, the moment you are putting a spinning action, the radial velocity at the center it is highest, and the radial velocity decreases as this material moves out, right. So if it is a shear thinning fluid, then in that case, if the velocity decreases, that means if the del u del y, the velocity gradient del u del y, if that decreases, then you have higher viscosity. So it becomes more difficult to flow, and also the evaporation is constantly taking place, because this entire material, that when it is deposited, this entire material was in one place, a blob. But now you are spreading it, you are creating such a high area, over which the evaporation can take place. So because of this evaporation, you will what will result is that this material will become more less of a liquid, right. So, automatically viscosity increases. So, what you find is that after you spin for some time, you develop an equilibrium thickness, and you find that the liquid is not moving anymore beyond a distance, all right. So, that is referred as equilibrium thickness. In fact, there is a formula for equilibrium thickness. The equilibrium thickness, I mean, this is an empirical formula, but at least this gives you an idea as to what kind of dependence you have, how this equilibrium thickness depends on the spinning rate, etc. This is the formula that is used for equilibrium thickness, where H is the thickness, C is the initial concentration, C is equal to initial concentration of polymer, omega is equal to angular rotation velocity, and k is some constant, and obviously mu is the viscosity. So, if somebody tells you that okay, you are getting equilibrium thickness, say after running it at say 5000 rpm, you are getting certain equilibrium thickness. If somebody tells you okay, if instead of 5000 rpm, if you would have done it at 9000 rpm, what would have been the thickness? So, using this formula you can calculate what would be the thickness. Can you tell me it will be higher or lower? It would be if the omega increases, then H would be automatically decreasing. So, the thickness would be lower, and obviously, if you have a Newtonian fluid, you expect that entire fluid to be just thrown out of the center. So, you cannot have the concept of equilibrium thickness. This can exist only for a non-Newtonian fluid and where the viscosity changes with evaporation of solvent. Once you are done with this, now I have another point to make here. This silicon material that has to be held in place. Okay. Now, if something you have to rotate something, say in a lathe machine, you have something called a chuck, mechanical chuck, in which you fit that plate, and then you rotate. Then you do the necessary operation on this. Now, here in spin coating, here the rotation speed is pretty high. Rotation speed is very high, and moreover, the wafer that you are working with is really thin. So, holding this wafer by a mechanical chuck is not very easy. So, there is an alternative method people have come up with, which is the use of vacuum. So, what they are doing is, this is basically, this part is connected to a vacuum pump. So, this place is under vacuum. So, outside it is atmospheric pressure. So, if you create vacuum, you can hold this wafer in place. All right. So, this part is connected to a vacuum pump. This part is connected to the vacuum pump, so that this wafer is held over this chuck, over this chuck by means of vacuum, and not by any mechanical clip or anything, because this wafer as such is very thin and it has to rotate at a very high speed. Now, once you are done with this coating, this heating of resist, this is typically followed, heating of resist at 70 degree centigrade for few minutes to evaporate 15% of solvent remaining to avoid formation of cracks. What does that mean? This you have achieved an equilibrium thickness. You have achieved an equilibrium thickness on the substrate material, but still 15% of solvent is still there. 85% got evaporated, and that is why this material became immobile, but still 15% of solvent is there, and that solvent has to be removed in a precise manner, because otherwise that solvent can come out at some other odd moment, and at that time it will form crack, because that solvent has to come out at some point. So, it has to be heated in a controlled manner, and that is done by heating the resist at 70 degree centigrade for few minutes to evaporate this 15% of the solvent. Now, there are various reasons because of which the spinning process can get into trouble. One is that these air bubbles in dispensed resin can come. Air bubbles can come in the dispensed resin if dispensed tip is cut unevenly or has defects. And air bubble means if this is the wafer, and you are expecting a coating of this wafer, uniform coating everywhere, and what you end up with is having small bubbles here and there inside the coating. Okay. So, the person who is running this, he has to be careful. The next point is, if dispense rate is too high or spin bowl exhaust rate is too high or resist on wafer for too long prior to spin, or spin speed or acceleration is too high. So, if these are high, then in that case you will see some amount of uneven distribution of this resist material on the substrate. So, there are these parameters need to be taken care of. Spin bowl exhaust rate is I mean, this is a new term I see here. Spin bowl exhaust rate is this entire assembly is put inside a spin bowl, okay, and then exhaust is collected. There would be, it could be possible that in fact some people, to ensure that there isn't any bubble formation and this liquid penetrates all over the surface everywhere uniformly, they put a little bit of vacuum as well, vacuum here as well. So, spin coating under vacuum, that is also another possibility. So, this is what they are referring as spin bowl exhaust rate. Okay. There could be another problem, which is fluid is striking substrate off center. Fluid has to strike at the center. If the fluid strikes off center, say here, this is rotating around this axis, but the fluid is striking here. So, what will happen? Then you will see a pattern forming within the fluid, a spiral. Instead of a uniform coating, you will find a spiral. Fluid has to be dispensed at the center, because the rotation, the flow of this resin over the substrate is accounted that way. Then insufficient dispense volume. If the volume that is dispensed at the center is insufficient, you are expecting a coating of certain thickness. Now, you have given the resin which is you have already decided an equilibrium thickness. You know that this is the speed, and at that speed, at this viscosity, I can expect this to be the equilibrium thickness. And if this is the equilibrium thickness, what should be the volume of resin you must have, that you need to calculate. Now, if you give less than that volume, then automatically what you will see is places of this substrate exposed, places of the substrate not covered by the polymer, and that will happen in a very erratic manner, because the entire material, see the way it is done. So, if in some places resin is insufficient, in that case the coating will also be insufficient, and so in places you will see the substrate exposed, not properly covered by the polymer. The last point here is that air bubbles or particles that may be present in resin or particles on substrate prior to dispense. So, you have to be careful that these air bubbles or particles, they are not present in the resin, because if they are present, then they will disturb this whole process of spin coating. And moreover, there could be particles sitting on the substrate itself. The substrate itself may have particles sitting on it, and that can alter the flow process completely. So, that can create problem in spin coating. This so that is why this substrate, prior to spin coating, this substrate needs to be cleaned, and there is certain protocol that has to be followed for cleaning the substrate prior to going for spin coating. So, this entire idea of spin coating is to make sure that there is a coverage of polymer over the entire substrate, and then it would be taken to the exposure step, where a part of this polymer will be removed, a part of the polymer will be exposed to light. So, one portion would be lit portion, and other portion would be dark, one portion would be lit portion, other portion would be dark portion, and then depending on where it is lit or where it is dark, that polymer will be dissolved, will be taken away from the substrate. Now, the exposure step, substrate coated with photosensitive polymer is placed in an aligner. Aligner is the mask aligner. That means, these mask has to be made parallel to this substrate. So, you have to make sure that there is a precise aligner that does this job. Luminous flux crosses the mask and hits the coating on the substrate. That is exactly what I said, right. Light of wavelength 300 to 450 nanometer is used. Luminous flux initiates reactions in the polymer, that is, it has to alter the solubility pattern. So, luminous flux initiates reactions in the polymer. Now, there are two types of resists. I said at the very outset that there are two types of resist. One becomes more soluble once it is exposed to light, and other becomes less soluble. So, depending on whether it is more soluble or less soluble, you differentiate these resist by calling it positive resist or negative resist. An example of positive resist is PMMA, polymethyl methacrylate. Okay. And example of negative resist is this is a trade name KTFR from this company, or SU8, that is also another well known name from another business house. Now, positive resist, the definition of positive resist is after exposure the polymer becomes soluble in a solvent as the light weakens the internal bonds. So, the exposed part is eliminated. All right. And for negative resist, after exposure the polymer becomes insoluble in a solvent as light induces covalent bonds between chains. So, in one resist light is breaking down the chains, and in other resist light is creating the chains. So, that is all that is how nature works. So, in case of negative resist the unexposed part is eliminated, and in case of positive resist the exposed part is eliminated. I hope this is clear to everybody. Now, there are other issues to this photolithography process. These you should have pointed out at the very outset. The other issue is that the half life effect during exposure. The half life effect is that opaque object produces shadow as well as penumbra. What is that? You have, I said that there would be a source of light, and then there would be a mask, and there is pattern transfer happening. Now, think of a light source and an object here, okay, and that is forming a shadow, that is forming a shadow. So, there would be a shadow here, that is what you are expecting, right, that is called shadow. If this is the object and this is the light source, so there would be a shadow forming. I am sure you have studied something called penumbra. There would be a reduced light around the object, because after all what you are doing here in this mask and this pattern transfer step is you are creating a shadow, you are creating a shadow of the mask that you put. So, once you are talking about this shadow and the light source, you will have this problem. So, what you are ending up with is basically half light around the object. You have defined the object very well, but around the object you will not have. So, you will have something called a half light. So, this is called half light effect during exposure. Okay. You can refer this penumbra and how this opaque object produces shadow. You can read this in this is a very preliminary course on optics. The first lecture probably this would be in initial lectures it would be covered. So, this is what this half life effect is. Also, there could be diffraction happening. Light is passing by a mask. Okay. So, there could be diffraction happening, and that can cause the reduced light or scattered light when it comes to the pattern transfer. So, these effects should be as small as possible. That is one point that you need to understand. The other point that you have is transparency of the resist. Light has to penetrate and modify the resist over the entire thickness of resist layer. All right. So, light has to penetrate the entire thickness of the resist. If it hits the upper portion of the resist and modifies the solubility, forms covalent bond or breaks covalent bond only at the upper part, but this resist itself does not transmit light, does not allow the allow the light to pass through it, then the lower part of the resist will not be exposed to light. So, this this change, this photosolubility, this effect will not be uniform over the entire thickness of the resist. You will say, what, this thickness would be very small. I understand, because that's why you are using spin coating. This thickness would be very small. However, whatever the thickness it is, this property of this resist material you have to ensure. Light has to penetrate and modify the resist over the entire thickness of resist layer. Then there is this choice between positive and negative resist. You may ask that I have a choice, now which one to take. Now, the practical suggestion would be negative resists adhere better to the substrate. Negative resists are more chemically resistant. On the other hand, positive resists show better contrast in photosolubility. So, these are pros and cons of these two resists, and people when they develop protocols, they develop based on these understandings. So, this is a typical protocol that is followed. I mentioned that at first you have to put a mask aligner and take the exposure. Prior to that, you have to have spin coating done, but I said that particles are not allowed on the substrate surface, because if particles are sitting there on the substrate, that can disturb the spin coating process and the coating will not be uniform and there would be all kinds of problems coming up. So, a typical protocol would be immerse the wafer in acetone in an ultrasonic bath to dissolve organic residue and then drying. So, take the wafer first, the silicon wafer that you have gotten 500 micrometer thick and diameter or the other dimension is 4 inch, and immerse the wafer in acetone in an ultrasonic bath. Ultrasonic bath the ultrasonic bath, the purpose is that it ensures that any dirt, any particle which is adhering to this substrate, that because of that vibration it gets dislodged. So, you put it in acetone in ultrasonic bath and make sure that organic residues are dissolved and then dry it. Okay. Then repeat the previous step with alcohol. So, that means instead of acetone you do it with alcohol. Some residues which would be going away with acetone, but some will remain. So, you ensure that you do it with alcohol itself. Now, then next it is you dehydrate on a hot plate at 120 degree centigrade for 5 minutes. Dehydrate on a hot plate at 120 degree centigrade for 5 minutes. The first 3 steps, the objective of first 3 steps that I mentioned, that means once in acetone, then with alcohol and then dehydrate, the objective is to ensure removal of contaminant from the wafer. So, that wafer does not have any extraneous material which can cause trouble later. Next, the wafer is coated with photoresist in spin coater, and that process I have already described how the spin coating works. So, once the spin coating is done, the system is heated to 65 degree centigrade for 1 minute and 95 degree centigrade for 3 minutes to ensure hardening of photoresist. Photoresist, it formed an equilibrium thickness because it cannot flow anymore. That does not mean that it has hardened. Okay. And you may say that okay, if I leave it on the table, it will harden. However, there would be always some harden, maybe it has hardened to the extent you want for the purpose you have, but it has not, the properties still continue to change. So, once you put it in this 65 degree centigrade for 1 minute and 95 degree centigrade, so you will ensure that the hardening is complete. Because otherwise there would be some changes going on inside that resist, which you do not want. You want that process completed when you go to the next step. So, system is heated to 65 degree centigrade for 1 minute and 95 degree centigrade for 3 minutes to ensure hardening of photoresist. Next step is exposure, and what is that exposure? I have already mentioned. You have the light and then you have the mask put by mask aligner, and then the exposure takes place. Next step is that the wafer is post baked to 65 degree centigrade for 1 minute and 95 degree centigrade for 2 minutes to ensure progressive rearrangement of material during thermal deformation. There would be progressive rearrangement of material, and once again as I told you, you want to ensure that all the rearrangements that are taking place, because it is a chemical physico-chemical process that is happening within this resist, and whatever rearrangement is taking place, let us have this completed and frozen, because otherwise a reaction will continue till in an asymptotic manner for a long time. So, you do not want that to happen, you want to wrap it up, freeze it and go to the next step. Okay. Next is the system dipped in developing solution for 3 minutes. What is this developing solution? Developing solution is that solution in which polymer is soluble, right. Many times it is potassium hydroxide, I think. The system dipped in developing solution for 3 minutes. System is rinsed with alcohol and dried with nitrogen. The system is heated to 200 degree centigrade for 2 hours. Again this process, this 200 degree centigrade for 2 hours, you ensure that all the rearrangements are done, completed, frozen. Now comes to the silicon. I mentioned that it is a silicon wafer. You can work with either silicon or glass when it comes to photolithography. Now, what is a silicon? I said at the very outset, it is a crystalline material. That means it has an arrangement. It has these atoms are arranged in a particular lattice structure, whereas glass is amorphous. So, that means one is dangling with the other, there is not a very organized aligned structure. So, silicon that you get in wafer is delivered in the form of wafer that constitute a monocrystal. Monocrystal means it is a single silicon crystal. I think I must point out what a silicon crystal looks like. The silicon crystal, it is basically you understand what a cubic lattice is. Cubic lattice means a cube with one atom at each corner. This is not silicon, but this is called a cubic lattice. Okay. Then there is something called a face centered cubic lattice. That means one atom at the center of each face as well. All right. So, this is called a face centered cubic lattice, FCC. Silicon is basically an interpenetrating network of face centered cubic lattice. Now, it is not that is not the end of it. It is basically, think of two lattices placed one over the other. Think of two lattices placed two cubes placed one over the other. Okay. Then you shift one cube from the other by 1/4 distance. If 1 is the distance between the two atoms here, you go by 1/4 distance, shift 1/4 on x axis, shift 1/4 to y axis, shift 1/4 to z axis. All right. So, this is basically an interpenetrating network of cubic lattice, where two face centered cubic structures, they are shifted by 1/4, 1/4, 1/4. All right. And the structure that you get now, it is extended to infinity in all directions. Then that is the structure of a silicon. Okay. So, it has a very organized alignment, and that now when we talk about a silicon monocrystal, we are talking about that material. So, monocrystal means it is a single crystal. Okay. So, this crystal is produced by well controlled crystalline growth process in clean room class 1 to 10 by slowly pulling a crystal from an ultra pure bath of silicon. So, from an ultra pure bath of silicon, this bath that material rotates and you get this silicon out from there, and this is a single monocrystal, that is a monocrystal. That means this lattice structure face centered cubic interpenetrating face centered cubic lattice, where two cubes are shifted by 1/4, 1/4, 1/4, that structure is retained everywhere. And then you cut it into slices. Slices are cut from a cylinder followed by atomic polishing phase. So, you get this silicon out from a well controlled crystalline growth process and then cut slices, okay, and then that one slice we are referring as silicon wafer. So, this is a single monocrystal of silicon. So, you expect that this face centered cubic lattice structure that I said, that extends to infinity. That means, there would be one, then there would be another one on top, then another one in the right side bottom. So, this is extending everywhere, extending, and these basically the wafer that you get is basically for having this crystalline arrangement. All right. So, I read it once again: delivered in the form of wafer that constitute a monocrystal, produced by well controlled crystalline growth process in clean room by slowly pulling a crystal from an ultra pure bath of silicon. Slices are cut from a cylinder followed by atomic polishing phase. Okay. Typical thickness of wafer is 500 micrometer, the other dimension is 4 inches. Two interpenetrating face centered cubic lattice network, you understand what that is, I just now mentioned. Okay. Side of one cubic face is 5.43 angstrom and highest density planes 111 form an angle of 54.74 degree to 100 plane. These 111 and 100, these are called Miller indices. All right. Now, what is a Miller? What is this Miller index? What is that? If you have a cube, suppose okay, and you form a cube here. Okay. Now, suppose this we focus on this plane. And if we look at where this plane cuts the x, y and z axis, okay. Suppose it cuts at say x bar location, then we write 1 by x bar as the x component of this Miller index. That means, what would be this plane? Typically, when it comes to a plane, we generally, if we assign a vector to it, we write it perpendicular to this plane, that we refer as that particular, we refer the direction as far as this plane is concerned. So, this plane cuts the y axis. Suppose this dimension is 1, suppose this dimension is 1, this dimension is 1 and this dimension is 1. This plane cuts the y axis at a distance 1, and at what distance does it cut the z axis, or at what distance it cuts the x axis? This never cuts the x axis, because this is parallel to the x axis. This never cuts the z axis, because it is parallel. So, that means you can say it cuts at infinity as far as intercepting the z axis or x axis is concerned. So, if I take the 1 upon the reciprocal of this intercept, I see that only I have y present there, x is 0, y is there as 1 and z is 0. These are the, so these particular 1 0 1 0 defines this plane. All right. So, you find out at what intercept it cuts the x axis, y axis and z axis, take the reciprocal of it, okay, and you see that the reciprocal of infinity is 0. So, you write this as 0 1 0, this plane. all right. So, this way you can define 1 0 0 plane, this way you can define how can you define 1 1 1 plane? What would be that? It is cutting the y axis at 1, cutting the x axis at 1, cutting the z axis at 1. So, how would that be? What I can think of is something like this. So, it is cutting all the planes. So, you have 1 1 1 plane. So, what you have in silicon is that highest density planes are 1 1 1. So, when you have these two face centered, when you have this face centered cubic lattice interpenetrating network of face centered cubic lattice, and when they are when there are these two interpenetrating cubes separated by this 1/4 unit distance away from in each axis, in that case you have highest density plane as 1 1 1. That means 1 1 1 plane in this crystalline structure is packed with atoms, that is the most packed with atoms, and this forms this angle 54.74 degree to 1 0 0 plane. All right. So, this is a particular feature which would be very important, because the way the atoms are packed, when you take this silicon substrate for etching, after all what is happening in etching? In etching, this silicon atom is reacting and the product is getting into the solution. So, if that plane is more packed with atoms, so it would be more difficult to etch that plane, whereas if some other plane is less packed with atoms, that plane will be easily etched. So, when it comes to the etching of silicon substrate, there would be an anisotropy developing within the silicon substrate. I will take this up in the next class. This is an interesting exercise, this photolithography, and we are taking the essence of these methods, and we will tailor this method for the microscale fabrication, for making the microscale devices. So, in the next class I will continue further with these etching process and how this crystalline arrangement affects the etching process. Thank you very much.